Hello, my name is Gunnar Epping, and here I'll be presenting a video abstract for a quantum geometric model of color similarity judgments. To begin, why study similarity? Similarity is thought to be a central cognitive process that plays a role in learning, reasoning, categorization, and language, just to name a few. To model and visualize similarity relations between objects, Shepard proposed the law of generalization. Here, objects are represented as points. As you can see, colors represented as points here in a metric space. And the similarity between two objects is computed as an exponentially decaying function of distance, where this pointwise geometric representation is estimated through multidimensional scaling. This work has been accepted as the default method with which to model similarity relations due to both its accuracy and spatially intuitive representation. Yet, there are several fundamental constraints that are implied by this approach that have been empirically violated. These fundamental constraints are the metric axioms. First being minimality, so the distance between one point and itself must be 0 or minimum. Symmetry, the distance between red and orange must be the same as orange to red. And the triangle inequality, which simply states the distance between red and orange must be equal to or less than the distance between red and any other point in the space and orange and that same point. The sum of those two distances. The Tversky has demonstrated that all three of these axioms can be violated, which posed a major challenge to the pointwise geometric approach. Out of the violations of the metric axioms, the most widely studied is asymmetric similarity judgments. According to Tversky's theorizing, the asymmetries in similarity judgments are driven by the relative salience or extent of knowledge of the two objects or concepts being compared. Now, the notion of salience has proven difficult to apply to different sets of stimuli, and extent of knowledge may work for conceptual stimuli, but it does not transfer well to perceptual ones. To investigate similarity judgments between perceptual stimuli across 3 experiments, we collected data where individuals would rate the similarity of a pair of temporally separated color patches. Here you can see one color patch is presented, then removed, and then the second color patch is presented, and then participants rate the similarity of the 2 color patches on a scale of 0 to 7. Do note, in one of the 3 experiments, we did not allow unlimited stimuli presentation. We instead altered it so that was only 250 milliseconds like the other color patch presentation, and the results did not change much. We identified several violations of symmetry in the empirical results, which the conventional multidimensional scaling approach cannot readily capture. If you would like to take a closer look, I encourage you to pause the video here. As an alternative way to account for similarity judgments, a quantum geometric model of similarity has been proposed, as it naturally accounts for asymmetries in similarity judgments. Please note, the quantum model does not rely on the assumption that the brain is a quantum computer. It merely uses the statistical structure of quantum mechanics. Instead of representing objects as points in a metric space and encoding similarity through distances, like in multidimensional scaling, the quantum model represents objects as subspaces of a vector space and encodes similarity through the angles between subspaces. Note, in this model, we represented colors using one-dimensional subspaces, which just look like vectors here. So how is similarity computed according to this method? Well, we theorize that individuals start in some initial state, which is then projected. If you're judging the similarity of A to B, it's first projected onto the A subspace, and then projected onto the B subspace. And then this length right here is converted to similarity using some monotonic function, just like how distance is converted to similarity using an exponentially decaying function in multidimensional scaling. Now, somewhere to assess the similarity of B to A, you can see these two lengths are different, which would result in asymmetric similarity judgments. To compare the two approaches, we fit several variations of the quantum and multidimensional scaling models to the behavioral data. Displayed here are the two-dimensional and three-dimensional color spaces that were employed by the quantum and multidimensional scaling models. As you can see, the results of our model fitting displayed. The three-dimensional quantum model notably outperformed the other models according to BIC. Note, BIC, the lower number is good, so that's why the three-dimensional quantum model was good. And additionally, without any alterations to the quantum model, the model predicted several violations of another metric axiom, the triangle inequality, and many of these violations were also identified in the empirical data. Overall, we believe that the quantum geometric model offers a viable alternative to multidimensional scaling for modeling similarity judgments, as it naturally captures asymmetries in similarity judgments while still providing a convenient spatial illustration of similarity relations.